If you speak a bit too softly, it won't pick up much at all. Okay, so the first thing we're going to do is drop from here and then play Kahoot. Okay, so again, every time we come to lecture, you'll need your phone or a tab in your browser. Okay, and you need to jump into Kahoot. So I'll just put the pin up, and you need to go into Kahoot.it. Okay, and register. Okay, and typically you have to gauge the size of the class and the number of participants online. So there are 14 of us online. Some of the people online are people in the classroom, right? So you have to discount that. So usually what I think is like, okay, I see about 30 people here, 10 people online. So roughly if we got about 75% of the class, then you can start. So you need about 30 people, hopefully who can come online. Okay, then we can start the okay. So just to make it clear for those of you doing support and you want to do Kahoot, basically you have to do what I'm doing, which is prepare a 5 to 7 question quiz. Okay, mix of easy and hard questions. Okay, and then the week after the lecture is done. So I'm doing the Kahoot for last week's, and you run it at the beginning of class. Okay? It should take no longer than 15 minutes because otherwise the lecture will never end. Okay, we'll get out of here at some ridiculous time like 30. Okay. All right. So I think we're going to start. All right. I'll pause. Let's go. Okay. So for this topic, we're going over week 1. So which methods can be used to answer the when to retrieve? Now, there may be more than one way, but there are a couple that we discussed. Confidence-based measure methods, classifier-based methods, LLM-based methods, and RAG-based methods. So give a guess. Again, this is not anything that we worry about getting absolutely correct. It's just a way for us to get some indication of revising what we've done. Okay. You have 3 more seconds. 2. Okay. So actually, when Haitao went through the slides with us, all 3 methods that are listed here are plausible methods. Okay. So what does when to retrieve mean? It means when we go and ask a system like an LLM to not rely on its parametric knowledge and instead to get documents or some other piece of data from a data store, right? And Haitao in this segment said that there are basically 3 different methods that we can use, roughly categorized. This is, I think, we're all our own categorization, right? So classifier-based method uses a machine learning model to decide whether or not to evoke one of the different ways of doing things. Like if I think that I need to retrieve useful knowledge, okay, then I have to use retrieval. So if it's something that the query explicitly says that they need to pull out information. So I could build a classifier just for this thing, right? Confidence-based methods are another thing, right? So we could use a confidence score to indicate whether or not I believe that my answer is correct, and then decide not to retrieve. Otherwise, if I'm not confident enough, I could execute a retrieval to get that done. Okay. LLM-based methods basically delegate the task of whether or not to retrieve to a separate LLM query, right? Judge that. And finally, RAG-based methods, well, we're studying RAG as a whole. So this is an element of RAG, question about whether to retrieve and when to retrieve. Okay. So again, sort of a meta comment, this is the type of thing that we would ask a person setting Kahoot to do. Okay, have some understanding of the question, narrate the answers and the options. Okay, so we have Y in front, Zaidan in second place, and Xindian Lu in third place for right now. Okay, what is a query browser? Okay, so is it a piece of networking hardware? Is it something that converts a query from one form into a more suitable form? Is it a triager that assigns a query to a particular answering technique? Or is it a component in a query reformulation pipeline? Okay. So most of us got this. A triager, as we were talking about in the first segment, is a system that decides which component is supposed to answer that query, right? Whether to send it to a fact retriever, whether to send it to a document retriever, etc. Okay, so the when to ask is part of that component as well. Okay? It's not completely wrong to say that it's a component of a query reformulation pipeline, because when we do RAG, many times we have to consider the retrieval system and what it's capable of doing. Okay, so for example, a retrieval system could be a Boolean retrieval system that just uses keywords. Okay, so in that sense, we might say, okay, given a query, I actually want to reformulate it to a specific form to send to that. But that is really more of a query reformulation component, which you as a query triage unit could send the query to. Does that make sense? Okay, so we could say that this brown box here could delegate part of its responsibility to a query reformulator that will then retrieve something from a data store. Okay, next. Okay, so Ada is on top. Shinken moving up one rank and Y in third place. Okay, what is multi-vector retrieval? Okay, so when query is converted each stage through multiple representations, could it be where n per token queries are used to retrieve passages? Could it be when a single query is vector average from its component word vector queries, or when additional queries are adaptively added as? Okay, so we have 26 answers so far. A couple more. Okay, so the answer that I got, and again, I'm not an expert. Haikao can rebut me, and as the subject matter expert in a second. I think it's where we take multiple queries that are all token-based representation. So if I have a query that's, say, n tokens long, each of those tokens gets their own representation and embedding. We send all of those queries out to the data store to retrieve relevant passages. Okay, then we get all those passages back. We still have to do something with them in order to generate the answer. But the idea here is we get all of those documents back first. We do it through multiple query representation. Okay, so you can contrast that with the single vector approach, which is what you standardly think of. You say, I have a query. It's represented by a couple words, and those words I'm going to condense down to a single vector representation, and which I'm going to send out to a IR engine to get back documents. Okay, so we covered part of these methods last week. Okay, but again, very, very shallow. Okay, I think over the entire course we're going to go into more detail. Okay, so Y is at the top of the scoreboard now. AT come up, a new ranking, and Zaidan has regained her position. Okay, our fourth question. What characterizes generative information retrieval? Okay, is it ranks, then retrieves? Is it a complement to RAG? Is it a single parametric model? Or is it end-to-end? So this is multi-select, answer more than one. So it's a bit harder because there are multiple right answers. Go ahead and match whatever one you think is correct. Okay, 1 second. Okay, so pretty much all of these are correct except ranks that retrieves. Okay, so ranks, you have to have documents to rank, right? So you have to retrieve those documents first. So that's why answer A is wrong. Okay, the other three are correct. In fact, the graphic that we showed shows that it's a complement, right? That you can do generative information retrieval and retrieval augmented generation combined, because there may be some queries that are better for one and some queries that are better for the other. Okay, and there's no stopping us from defining some hybrid which uses a little bit of both. Okay, in the discussion of this, the slide also says that maybe what we can do is, instead of doing retrieval augmented generation, we just trust the language model actually do information retrieval for us, right? That means instead of going out to Google, you just ask ChatGPT for everything, right? So the idea is that single parametric model, that neural network, will have all the knowledge imbued in it, right? And because it's a single parametric model, hopefully you can train it end to end. We don't need to go to Google anymore. Everything is inside a single parametric super AGI type model. And we just ask that, and it can do everything. It can answer queries for you, but it can also recite documents verbatim. So if there's a web page that's seen before, it can tell you exactly what's on that web page, right? Which satisfies the need for information retrieval. Okay, Y has regained their top score. We have B, C, Y, and Ada in second and third. And our last question for today is, in RAG optimization, what is the one method for retrieval retriever optimization? Is it called replug, called FID, or FID light, or is it called smart RAG? Okay, this is a question I really didn't like, but I ran out of time to compose a better question. So my apologies for that. I had 30 minutes to come up with our quiz. Okay, so you've got 10 seconds. Again, if you have slides from 01, you can always take a look at them on your computer. Okay, so the answer is in fact replug. FID and FID light, I did spend a little bit of time on, but they optimize the other part of it, which is optimization of the language model and not so much the replug. Okay, so we didn't have a lot of time to go over that second half, but I'm sure we'll have more of that. Okay, so today we'd like to congratulate Y, ET, and BCY for their performance today. So let's okay. So I'm going to start with that. So this is basically what you need to do if you want to do it. And we'll go to our slide. And so I would like to invite the lecturing team to come up and introduce themselves. I'll just slideshow them. Okay. So those of us in the audience, please welcome our lecturers, Yajing Yang, Ervin Teo, Yajing Yang, Jiaying Wu, Sahej Agarwal, and Benjamin Chek. Who's our starting lecturer? Yeah, you can just click that away and say start. That's fine. Cross that out.
Right, so it registers. Okay, good. That's right. So I guess we're gonna start off by maybe clearing some foundations of large language models, and I guess we're going to do this a bit atypically, right? Usually large language models we just introduce them as is, but then the course here is really about retrieval augmented generation. So we're going to color most of our introductions based on that. And I guess for this week, you'll be hearing from all fellow lecturers that actually we are going to be basing most of our presentations off of the bottlenecks that were identified in the first week of this course, right? So I guess I'll be the one to give the colored sort of overview, and you can see that the other lecturers will basically be documenting how it relates to the bottlenecks that we identified last week, right? So I guess we'll start with just probably a gentle introduction. I think this might benefit undergraduates a bit more because I'm not sure how familiar we all are with large language models. So normally we are looking really at a very literal decomposition of the term, where we are looking at people who have decided to basically adopt a sort of causal and conditional kind of model for natural language tokens, where we don't really ascribe any sort of meaning. We don't color our perceptions. We just start with probability. What is the chance that some token comes in right after all these concepts that I've been feeding in, all the sentences that came before what I'm about to say? That is the mental model that people are going with here, purely statistical. And I guess it's been quite a recent phenomenon that we got lots of success in scaling language models to, I guess, loads of parameters that require really large scale hardware to actually train up and create, I guess, a parameterized and a conditioned general form of this token distribution. It is really just at its finest, it is just a single token distribution. There are sampling methods that go beyond the single token, but the most fundamental language models, they operate on a probability distribution of the next token. So that it kind of explains the formula there. So we are really going to, I guess, share a bit about some of the training processes that go behind the language model, because I guess a lot of care has to be taken when training these models, such that we can actually get a better understanding of how retrieval augmented generation actually gets affected by some of the foundational processes that some of us may take for granted, whether it's because we lack the resources to actually train our own models, or whether it's because we're just not aware of them, and hopefully we can actually eliminate the latter part. So most language models, again, everyone has their own way of training a certain language model. I'm just going through the archetypal and the modern, quote unquote modern pipeline, where we have pre-training, where we do the usual. I'll elaborate more on this later. We're going to do the usual sequence to sequence training, and there's also some supervised fine tuning where we actually have a little more structure to the data, right? Instead of purely just having the model ingest a massive corpus. And finally, I guess this is also something that appeared a few years later than the other language models, right? We've got language model post-training, which actually uses a variety of techniques, either to put some finishing touches onto the language model to make it more palatable for use. So things like this would be output formatting, output structuring. It could be reasoning for mathematics, or it could be ethical guardrails for safety usage in downstream applications. So I guess we're just going to go through each of these in a little bit of detail. And at the end, after explaining the full pipeline, I'll try and contextualize what challenges are for this particular model, or these particular models, or design choices when it comes to retrieval augmented generation. So as I mentioned, right, we do have pre-training where we really just collect as much data as possible, right? So the thing here is that the data can be somewhat clean, but usually we don't really 100% care. We just want the scale. Scale is most important. Which is why we get, I guess, if you really went to look at some of the data sets that people use for pre-training, it could be things like just a Stack Overflow website and all the ugly responses. It could be something as ridiculous as a math formula, and then some nonsensical text before the user. It doesn't matter. The point is that we have volume data, and I guess that's what people have prioritized over the exact quality. Mostly because we are operating at such a massive scale that it becomes impractical to actually care about to curate the data one by one. So we're looking at data that is intractable, even if, let's say, you hired the entire population of Asia to go and curate the data set for you. So that is what we really mean by massive scale. And obviously, we are also not going to, unlike in supervised learning, for example, we might not use supervised methods. We might not use gold standard labels because, again, we're not going to have people to invest so much effort into basically put investing all our efforts into writing the correct answers. You know, we just want understanding. We just want some kind of probabilistic model that would be implied by all the natural language that exists out there on the internet. So we're going to use something called self-supervised training. And I guess the idea is really simple. So let me just erase some of the working here so I've got a little space to work with. Self-supervised training, instead of the gold standard labels that I mentioned just now, we're going to look at perhaps a sentence like tends to use massive terabyte scale corpuses. We're going to look at these, maybe each word is a token. And what we're going to do is we're probably going to feed the language model just this part, right? Terabyte. We're going to stop at terabyte. What happens is that we're going to give it the red color, right? And we're going to have each position be able to predict the yellow color portion. So if I just make that clearer, these are actually multiple tokens. I want them to be able to do something like this. That's kind of how pre-training works. And really that explains the really strange formula that you see at the bottom. I'm mostly speaking for the people who may not be able to pass this very dense formula here. So the name of the game really is to maximize the likelihood that to maximize the likelihood that for any snippet inside the language corpus, this thing, the true next token, the true next token is actually identifiable, and it is the most likely one. So that is really what we're going for here. And one of the interesting things is that we've actually seen that pre-training is potentially responsible for most of the reasoning capabilities, or rather, it has a sort of perhaps it has a sort of counterfactual relationship. Like at this point, it's still not it's not a closed case, right? But the ongoing hypothesis is that we do have reasoning capabilities coming from this particular stage of the model. So if your model doesn't have, for example, math problems in the training corpus, most sources that I've seen would expect that the resulting language model is completely incapable of doing mathematics. So that's kind of what the role of pre-training is, right? To obtain rote understanding, to basically familiarize it with the rules of language. And some simple procedures. In words. I think you should be able to know that we can actually imbue some reasoning, we can imbue some task capability just by language alone, because that's how we've been communicating with each other. I can instruct you, I can teach you something new. So why can't I teach something else that conceptually understands language, a new concept or a new procedure or a new capability? So that's really what we're doing with pre-training here. Then what happens next is that we're going to, once we've had a model that does pre-training, this process, even if you have massive data centers, it will probably take you weeks or months just to come up with this model. So typically, unless you're one of the biggest, you own one of the biggest compute resources in the world, you're probably not going to do this. Or you're going to do it on such a small scale that it won't matter. And so what most people do instead is to try and do fine-tune. Supervised fine. Let me just next slide real quick. And this is basically most people's answer to the fact that language models are way too big for them to reasonably create from scratch. And it's just as well that most language models are really, really good at being fine-tuned. They lend themselves really well to fine-tune. And I guess that is attested to specifically in a paper in I guess Instruct GPT paper, if I recall correctly. I have it cited somewhere else, so unfortunately it's not here. But Instruct GPT is probably one of those that shows you like, okay, I cannot only use just supervised fine-tuning to human preferences, even though they use reinforcement learning to cover later. GPT-2 was also able to use supervised fine-tuning for things like summarization and as well as I guess comprehension. Like let's say I believe everyone here has done like comprehension exam papers before, where they ask you to read a passage and they ask you some questions. So comprehension is also one of those things that you can do. So large language models with a little bit of structure in their new supervised corpus, right? This one requires a little bit more supervision because I need a specific format for Q&A. I need a specific format for I guess alignment tuning as well. So it's a little bit more involved than just pre-training, where I just throw as much text as possible. I got to throw text of a specific format here. But once I'm done with that, it turns out that large language models are surprisingly capable of doing a lot of the traditional natural language processing tasks that were done so far, right? And the kicker is actually when people say continual training, when people say fine-tuning, they usually talk about full parameter fine-tuning, where they enable gradients for the entire model, but it doesn't have to be the case. You can actually just use parameter efficient techniques like LoRa or QLoRa or any of the multitudinous techniques that exist out there. I'm just writing one for awareness, and so that if you are curious, you can go and Google yourself, right? So the key part here is that the structured nature of the supervised corpus makes it a lot harder to produce, but it also provides better, more structured results. So let's say if you've got someone who wants to do a math problem, you ask the language model and it just gives you the answer straight. But you don't want that. You want it to give you the working, to explain the reasoning, and that's probably when you might use supervised fine-tuning. Although nowadays people use that more for content moderation and stuff like that. So we're also going to go into one of the more recent additions to the training pipeline, which is actually post-training, right? So all that before, we've been using the causal objective that we established in pre-training. But in post-training, the situation kind of changes, because at this point, the people who have considered the post-training problem most likely have access to very, very performant models already, at least in terms of generating coherent text. What happens now is that we got to have models that are capable of doing things like reasoning, models that are able to perhaps do complex tasks like playing. I guess if you guys have ever played Kahoot, it's this game where you've got a bunch of numbers, right? And then you've got plus minus times 5. And you're supposed to make like a new result. So this is a kind of problem that requires sophisticated reasoning. Even though it just involves plus minus times 5, it's got it requires some backtracking behavior. It requires some trial and error for the harder addition tasks. So for here, it's pretty obvious that 9 minus 5, for example, times 8 would give you 32. But perhaps a language model with no concept or little concept of mathematics would take some time, would require to, for some people who are starting to take introduction to AI in US, right? This would require a tree search, exhaustive tree search. to come up with the answer. You could do some pruning, but the idea is there, right? You're not running away from backtracking. You're not running away from trial and error. And turns out that this is something that language models are pretty bad at, which is where post-training comes in. So this is in fact one of the most methodologically diverse training stages in most language model training, right? We've got a lot of different approaches actually. A lot of people normally think of reinforcement learning from human preferences. That was common because it allowed people to rank preferences instead of telling models exactly what to say. So in terms of giving responses that were in line with ethical principles, helpfulness, harmlessness, and honesty. Right? These are really, really murky concepts that you would be able to imbue into the model through, instead of curated examples, handwritten, painstakingly written examples, you could actually, sort of code for these principles by just handing texts to human contractors and asking them, is this honest? Is this helpful? Is this harmless? So the burden changes from writing into simply asking questions. So it's a lot more scalable. And that's why human preferences with a bit of statistical modeling was favored, especially for things like response quality, response clarity, and of course, the alignment that I talked about just now. But I guess recently, there's also been a little bit of a hoo-ha about, okay, it's more like last year, but it's still pretty recent. There's been a little hoo-ha about using rules-based reinforcement learning to actually train large language models to do tasks like countdown that we mentioned just now. I probably shouldn't have erased that. That's my bad. So we're going to look at reinforcement learning with verifiable rewards to do tasks that require more sophisticated behaviors, logical deductions, right? First order logic. World modeling, where the language model is able to understand hypothetical scenarios. Like, for example, Alice and Bob are in a room. Who is in the room? So that will be questions that are very easy for you to answer, but they are not questions that language models could probably answer, especially if they get more complex. Like, for example, now Bob leaves the room. Is Bob still in the room? Or is Charlie still in the room? Completely unrelated questions. So even though, and as long as the idea behind verifiable rewards was not really that we have this new and complicated setup to train language models. In fact, it's quite primitive by all metrics of language model training. But the idea was that we are actually able to in reasonable time train models to have superlative performance on things that we thought we humans find hard ourselves. Things like mathematics, things like Sudoku. And I guess recently, if you guys heard the news about about testing models from OpenAI, and I don't remember who else, I think Google DeepMind, they solved they attempted the year's IMO contest, and both models got gold medals. So it's that kind of thing that really surprised people about such a seemingly simple thing, right? So it's really simple but effective. And of course, there's also more unorthodox approaches, such as direct preference optimization, and a more recent work about LLM self-code, which actually allows it through zero-sum games to basically prevent things like reward hacking. I won't go into the weeds here, but these are reliable and zero data methods of actually doing reasoning capabilities. But I mentioned just now that pre-training actually was responsible for imbuing capabilities. And this is really where the hypothesis of those people who made that same claim continues, right? Because most people suspect that actually what things like RLVR are doing and RLHF, what they're doing is they're simply drawing out what was already there. They are simply making the likelihood of good response go up and nothing more. So that's something else that we might want to take a little look at. It's also an open question, but I won't go too much into it because it is, I guess, a little bit tangential when it comes to retrieval augmented generation. What's really important though is that now that we understand this process, we should probably start to appreciate just how complex some of the interplay between most of these components is, right? Just even in like a very simple model, we've already had 3 steps and so many choices. 3 steps, so many choices, just to do a simple task of training a language model. We need to be really careful about things like our training regime, our implementation details. The devil's always in the details. We need to be really careful about and of course, we're not completely aware of how these seemingly simple choices can have really big knock-on effects on language models themselves and their ability to do knowledge recall, things like factual recall, knowledge recall, and their ability to scale and update with time, right? So we've got things like data quality. You already know that language models are using this data to sort of feed into themselves, and the knowledge gets fixed into it. During training. And it will not update easily. It will take quite considerable effort in order to fix. This is also true if you start adopting seemingly, interchangeable choices, even things like your position embedding. I know that there are some more, we used to have this big problem with non-context windows, which motivated retrieval augmented generation to begin with. It used to be that it was very difficult to have really long, the language model comprehend really long passages because it would just either drop some of the information, it would lose significance, or it would basically have trouble trying to recall any information that was perhaps a little further away. So even things like architectures, even though like 90%, that's just a number that I'm throwing out there, I don't actually have data to back that up. 90% of models are transformers, language models are transformers. We also have alternatives that are trying to basically change up language model training paradigms. And they also have their own host of problems. Things like memory, things like recall over long durations, long context windows. And even things as fundamental as attention mechanisms. I wanted to talk about attention, but I don't think I have the time here. I just want to give people awareness of some of the alternatives that exist to our so-called canonical QKV attention. And that's why I put them in slides. Even test time tweaking, your prompt engineering, things like that, they can have gigantic knock-on effects, right, on things like test time performance, whether your model is able to properly recall tiny details. And so I think that is really what we should take away from this, right? The process of language model training is really complicated. It has unexpected knock-on effects on things that I mentioned just now. Long context performance, for example. The training data that was burned into them, right? Factual accuracy, also the same thing. nowadays people are using language models to start calling tools, where it's an abstraction where you start asking the language model to basically be the brain in an artificial body. Even this reasoning capabilities that would allow it to make such decisions is also becoming a problem that perhaps we might be exploring in this course. And so I guess in summary, we're looking at a really complicated process and unexpected knock-on effects that result in two main problems. The two main problems are, of course, what I mentioned just now, which is over-memorization. We know that language models are huge by definition. But it also means that they tend to accidentally memorize stuff. They tend to accidentally, let's say you gave it the first few lines of Don Quixote, it would accidentally give you the entire thing, which is okay if it were classic, but not if it were a news report or some kind of intel report by a company that they might still have copyright to, right? And it is still extremely difficult to start sort of filtering this knowledge. In fact, if you see just how difficult it is by looking at these papers, you know just how naive it might be to try and do things like unlearning, editing the things that LLMs have memorized. So I guess that's what we are really going to be. And I guess that's what most of the other presenters are going to be talking about. It's challenges that fundamentally stem from, I guess, these two most important consequences. And well, if there are any more, and I probably missed them out, then they could also be topics for the future, right? So really just to show you how it specifically manifests, we've got things like hallucinations, we've got things like the alignment tags. And we've got, because the knowledge is burned in, it'll be really difficult to actually adapt the models to new scenarios. Like let's say it goes from 2024 to 2025. How am I going to adapt? And I think that is, having that understanding of how language models work and how they're trained is really going to help in, I guess, the next few segments that we're probably going to discuss. So I think that it's time to maybe hand over to some of the other lecturers who will be talking about, language models as they have bottlenecks in terms of information.
Okay, let's thank Ervin for his.
That was Chuen Yang and I'm sorry.
Yajing Yang, sorry.
Yeah. So I'll be talking about the first bottleneck, which is the prevalence of factual errors.
Okay,
So
before we go there, just to make it clear, we are not just in lecture, we are a reading group. So please go to the general channel if you're on your laptop. You can go also look at the slides, pick up the papers and read them while the lecturer is speaking. And if you have questions, please raise them up. You don't have to raise them orally, you can write them on the channel if you don't want to disturb the lecture. But it needs to be something where we're all actively engaged, okay? So if we have a shorter lecture segment, like Chuen Yang's segment was pretty long, then we can supplement it with discussion. Okay? It's better if it's more interactive.
So let's talk about two main terms. So factuality versus hallucination. So factuality is the ability of the LLMs to basically generate content that is factual and consistent with world knowledge, whereas hallucinations are just content that are like not grounded. So they are either listeners or so hallucinations can be factual as well, just that it can either be off topic or more detailed than what is requested. So this is why it's known as a factual hallucination. So let's take a look at some of the examples of factual errors. So this paper talks about a fact score, which is one of the ways of evaluating how factual long form generation is. And they test this by generating biographies with 3 different LLMs. And what they found is that the generated content is actually full of errors, and as the length of generation increases, actually more and more errors start to appear. So we can take a deeper dive into how they actually compute this fact score. So this is an example. So for example, the sentence they had is at the top. So this one. So Bridget something is an American actress, model, and producer, and so on. So what they'll do is they will break this down further into atomic facts. So atomic facts are just sentences that convey a simple, or sentences that convey a single fact, and they will test whether this is grounded in like a source instead of So this is how they calculate the score. And second example is with document summaries. Document summaries. So with document summaries, you want the generation to be faithful to the text that we are generating the summary on, and also factual. But what happens is, based on this article, when testing these summarization capabilities, it was found that hallucinations occur in more than 70% of the summaries, and 90% of these hallucinations were actually wrong. So there's some caveats to document summarization. Where regarding the faithfulness and factuality of document summary. So as I earlier mentioned, there are things, or rather, hallucinations can be factual as well. And with summaries, we tend to want to like summarize this document in our own words, and this can be the same for the LLM as well. So something that there's still no consensus on is whether these summaries should have no hallucinations at all, or if there's some tolerance or threshold for factual hallucinations that help to bridge the gap between different content. So for example, for this one, they actually they try to generate the summaries based on a single sentence. So just something to think about. So what are the causes of factual errors? So firstly, there's inaccurate or outdated training data, ambiguous prompts, and lack of specificity. So this refers to when we don't actually have, or rather, we have poorly phrased queries, and then it's more difficult for the LLM to actually answer our questions because there's multiple different interpretations of them. Thirdly, there's the limitations in retrieval and knowledge retention. Next is overgeneralization. So this is generating responses based on the closest related patterns instead of actually generating a correct answer. So earlier we talked about how there are statistical models. So this could be one of the reasons for factual errors. And lastly is errors in knowledge integration, which refers to when we have like during the pre-training steps, we integrate knowledge from a lot of different resources. So the LM may struggle to reconcile these if they have conflicting information. So we have some examples here as well for some of the causes of factual errors. The first one is with long tail knowledge. So long tail knowledge refers to knowledge that is less represented, or rather less common in the dataset. So based on the graph here, we see that as the number of relevant pre-training documents increase, the accuracy of the model also increases as well.
Can I ask all of you, which one of this case here, which one is it related to on the last slide? On the last slide that Ervin presented, there were 5 different causes, right? Any takers online or in the house?
Limitations in retrieval and retention.
Right, so there's clear limitations there, because you have a lot of data that's going in, and unless it's repeated many times, models can forget because the probabilities associated with that common path might not be well paid. Right? Any other ones that you think long-tailed information relates to?
Maybe errors in knowledge integration.
Okay, can you be more specific? Like
Yeah,
why
so-
that might be?
So like now that, okay, so let's say there's some topic which is in a data set which is less proportional as expected to other, as opposed to other topics. So the distribution of that specific topic would be less, as in it would affect the main distribution less. So that's like an error in knowledge integration.
Okay, maybe in part. Yeah. So when I'm sure Ervin is going to give us examples of errors in knowledge integration later. So we can pay attention to that, especially when there are several documents that overlap. There can be cases where the generation puts them together incorrectly, right? So we'll see that later.
Okay. The next example is with co-occurrence biases. So this refers to the LLMs comparing frequently of like words that co-occur together, which often override the correct answer rather than actually generating a correct answer. So one of the results from this paper was that it was observed with this model that a word with higher co-occurrence overrides the correct answer in 38% of the failure cases. So yeah. And the next example is with non-parametric memories actually misleading the LMs. So in cases where there's fewer documents, so from this graph here, the dotted line ones refer to retrieval augmented LMs, while the ones that are not dotted are just the normal models. And we can see that as the popularity increases for the entity, the parametric memories actually outperform the non-parametric memories. So over here, when there's a small number of related documents in the pre-training set, having a non-parametric memory, so having retrieval actually helps with the accuracy of the response. But as the number of relevant documents increases, this actually can impede the performance. And they hypothesize that this may be because the retrieval results are not always correct or helpful. So how can we improve factuality and what are the challenges with it? So there are 4 different ways that we can do so. So first is scaling the data set. So there are 2 ways that we can scale the data set. So one is either collecting more data, or the other is increasing the diversity of the data set. So what they actually found is scaling the data set by moderate factors, so like 5 times, usually only results in small accuracy gains. But and whereas for increasing the diversity, it may not actually significantly improve the accuracy, as many of these data sets are already correlated. The second one is scaling the model. So what the paper found is that you actually have to scale the model quite dramatically, over like 1 quintillion parameters to achieve like a human level accuracy on long tail questions. So it's still a struggle to actually have like parametric memory with regards to long tail questions, just because of how rarely they occur and like the difficulty of obtaining the data set to train the model on them. Next one is modifying training objectives. So earlier we mentioned that having like a larger data set. No, sorry. So how do I say this? Okay, here is modifying the training objective refers to changing how we actually train the model on the data set. So by reducing the data size, so let's say we want to train the model on a specific domain only. So that way we can use the data size and actually increase the number of epochs that we run this training so that the models can memorize as much as possible. So rather than having as large a data set as possible and just running one epoch. The last one is retrieval augmented generation. So earlier we explored the example where non-parametric memories actually impede the accuracy. So one way to combat this is with adaptive retrieval. So the way they do it here is they try to set a threshold for when to use parametric versus non-parametric memories when trying to answer questions. So this can actually improve the efficiency of the inference as well. Lastly, I just want to talk a bit about multimodal LLMs. So for here, we have again 3 different types of factuality. So one is incorrectly claiming the existence of certain objects in the image. So existence factuality. Next is attribute factuality, where they can identify the color of a car incorrectly. The last one is relationship factuality, and this talks about false descriptions of relationships between objects. And the mitigation for these is first, it's fine-tuning based methods where they collect specialized data, so either human annotated or more specific data on the content that they want to generate on. And the second one is inference time correction, where they basically correct the output generation.
Yeah, I'll say we have a lot of people in NUS doing exactly the last slide. So some of them are in this room. So we'll hear from them later. So let's thank Ervin for.
Hi, Miss. Can I switch to my own computer for
You
presenting?
can present from your deck.
Yeah.
So you're on the right place. Yeah. So you can screen and you can share. Oh, Yajing, can you share screen?
Sure.
Yeah. Yeah. If you want to take a toilet break, go right ahead. So Yajing, you can start because I think we're running a little bit behind lecture time.
Sure. Am I sharing properly?
Yeah, I think everyone you here can hear you. Anyone have any difficulties? Okay, all good. Yeah.
Okay. Yeah. So this is Yajing from WING Group, and so today I'm going to talk about the. Sorry. Okay. Can you see the slide that I'm presenting? Sorry.
See slide 36, challenges 4.
Okay. Can I go backward? Okay, yeah. So I'm going to talk about the difficulty of verification or for LLM generated content. So let me start with the importance of verification. So verifying the output of LLM is crucial to prevent misinformation and ensure reliable deployment so that the user can rely on the information provided with factual correctness and consistent and predictable also without harmful bias and or dangerous content. But there are a few challenges for verifying those LM generated content, starting from the nature of the language model, which is a black box nature, and also the dynamic nature of the truth or knowledge. And then I also cover the contextual, the difficulties in for verification in terms of contextual understanding and requirement of deep domain knowledge, as well as the ethics and biases verification of the content. Let me start with the first one. So the black box problem. So essentially, is a probabilistic language model. So it's not non-determinism. So with the same prompt, it could produce different and factually inconsistent output, making it difficult to perform consistent verification. And for and also the black box nature prohibit us from explaining why an LLM produce a specific output, and the lack of this interpretability makes debugging errors or understanding the source of the hallucination nearly impossible. The second challenge is about the dynamic nature of truth. So, like the example here is some answer could be correct at a certain point of time, then the so-called right answer might be changing along the time, like the answer to who is the US president. At a certain point of time, it will be Barack Obama, then Donald Trump, then Biden, then now back to Donald Trump. And the model also don't provide a direct link to the source where its information is coming from, like what we have for a publication. So making it impossible to check the origin or authority. Verifying the third challenge is about contextual understanding and domain knowledge requirements. So like the example showing on the right, where LM was trying to answer the question about describing the liver abnormalities in this CT scan, then the LM was trying to answer like the liver appears to have multiple small dark colored masses, but in fact this CT scan is not showing the liver. So in this case, it requires a deep understanding of the context, like what the user is asking for and the content of the image with a deep knowledge, domain knowledge. And some of the claim could be also vague, like it could be like many people believe that. Then in this case, it's also going to be difficult to verify against. The last challenges I'm going to talk about is about ethics and biases. So LM are from LMs inherit and amplify the bias from their training data, and the verification system themselves might also impact by those biases, and then this case will create a systematic blind spots where the bias or the ethical issue won't be able to be spotted out. So one of the figure on the right shows an example of like gender biases. So it shows like for the same amount of for each of the large language model, how many percent difference of the model generations use a gender specific word compared to their counterparts, which are from like a journal or news articles. Yeah, and such ethical bias could be subtle to be detected, and then and also it could be also depending on the culture and linguistic differences, and the 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 biases inherited from the training data could impact both the model as well as the verification system. Hence, won't be able to detect those. Yeah, that's all from for the part of difficulties of verification.
Okay, that's thank Yajing for her presentation. That's the next part. So again, you can follow online in Slack some comments and also work on bringing up your points, because again, it's really important to have more dialogue. So you can do it in Slack as well.
So, can I just have you guys raise your hands? Who of you have used GPT-3 and GPT 3.5? For day-to-day work, just, can you explain this sort of thing? So remember back in that day, they had this concept called a knowledge cutoff, where in the sense the model would not know anything beyond, let's say, 2022, 2023, or something like that. So during this kind of scenarios, there are methods in which we can kind of adapt the model to new situations. So it is usually in three categories as per this research paper: continuous learning, model editing, and retrieval-based methods. Since this course is about retrieval-based methods, I will not be explaining them, and will mainly focus on continual learning and model editing. So before we do that, let's understand a bit of stuff. So let's say I have an LLM model. Let's say Yamma 27 billion. So this model at floating point 32 will take 27 into 4. That is about 108 gigabytes of VRAM. From those using a laptop with a GPU, we know that VRAM is very, very expensive, and renting out a server is going to be even more expensive, energy consuming, etc., which we'll cover in the later section as well. But just to give you an idea, this is, by the way, just the forward pass. It is going to be very, very expensive every time we fine tune or basically even do a forward pass with any big model. Now I'll explain what continual learning. How does this? Yeah. Continual learning is basically where we add new facts at a very large scale to the model's knowledge corpus. It maintains the model generalization, and it can be used for several use cases like domain adaptation. Let's say I want to adapt a model for the medical domain, for the legal domain, or let's say adapt a model for NUS. Then it can be about time related updates, like I want to update the latest facts, like what is the Google population right now, etc. And in some cases, adding new knowledge, new skills, and linguistic related knowledge. So what happens with continual learning is this big issue called catastrophic forgetting. So going back to the 27 gigabyte model, so 27 billion model, that is 108 gigabytes. Can we expect that only 108 gigabytes is needed to store entire humanity's knowledge? Of course, we cannot assume that. And so there comes this issue of catastrophic forgetting, where basically the more you fine tune a model onto new data, we slowly lose the original data, and it starts to create an issue for us. So I found this research paper where they were actually trying to estimate that when we're adding a new fact or a new item into the knowledge base, what extent is the previous information lost? As you can see, this is a very complex formula that I did not 100% understand. But based on the explanation of the paper, using some of the fine-tuning methods for only about a 737 million parameter model, we are losing to a very large extent the previous knowledge that was already in there. So just imagine I'm a very advanced AI researcher trying to make a model that will help me cure cancer. But the model starts to forget what is 1 plus 1. Obviously, I wouldn't want that. I care about the life of my patients, and would again have to mix in the original data so that the model doesn't forget that. Again, how do I get the original data? Because the text corpuses are huge, and I will basically waste a lot of time, energy, and everything trying to figure out what data do I try and retain. So there was one method that I found that kind of tried to solve this issue, where we basically to the CL data set, we try and add synthesized sentences by the original model so that it retains some of the information from before. But again, the forward pass is expensive, and generating the sequence will add more computational expense, more energy consumption, and more time on a GPU server machine, which is if you have the money, you can do, but it's very, very costly and not good for the environment at all. Then comes model editing. Model editing, if I use an analogy, is like going through a bit of a surgical precision where we try and insert or alter small groups or a small number of facts inside the LLM transformer. So some of the methods that I used are gradient-based methods. And okay, why did that happen? Here, sorry. Yeah, gradient-based methods and locate and update-based method. In gradient-based methods, we basically try and train a small MLP inside the model, which kind of helps us to alter the sequence it generates. As we know, LLMs are basically a form of autocomplete from the previous sections. And in locate and base methods is where we try and identify the particular weights and neurons of the model that are responsible for the particular sequence generation, and we try and alter them. Okay,
Yeah, I have a question. So, like, regarding locate and update, right? If you find the neuron clusters, is there a risk that if you modify those, it will affect like other facts?
yeah, I'm coming.
Oh,
to
okay.
that.
Yeah.
So basically, gradient based methods are again not going to 100% solve the issue of me not having to require that amount of compute. It will still require a huge amount of pre-compute, but the amount of gradient calculation gets limited to a few layers and a few weights, which decreases very significantly the amount of compute, the amount of virtual RAM that we need to edit a model. At the same time, locate and base methods also focus on a similar thing where we are trying to identify what is the origin of this issue. For both of these methods, again, large compute is needed as and when we go to bigger and bigger models. Okay. So now these also have their own bunch of issues. So we can unknowingly alter other knowledge of the model. Again, same as before, I don't want a very advanced model not knowing what is 1 plus 1. Then some of the general capabilities of the model get slowly eroded. We slowly and lose the abilities that the model gained by its pre-training and the post-training processing. Also, it might, if you don't end up doing the model editing process well, it might end up creating internal conflicts. Let's say there's a conflict that we all know that NUS is the best university in Singapore, but there might be an internal conflict arising that they say NTU is the best university in Singapore, which we don't want happening, and the model is leading to hallucination. Also, imagine that I'm trying to make a model that knows each and every fact about computer science out there. So Google, I just asked ChatGPT that about 2.5 million papers are written every year. Imagine going through the process with each and every statement inside a paper, dealing with self-attention that is of O(n) square complexity. That's a lot of compute, a lot of time, and a lot of effort that may or may not be 100% automated that you have to do. At the same time, during all of this, you have to verify and keep verifying at each stage that is the previous information retained or not. Do we want to go through this method or just switch over to RAG? Now I would pass on to the next section.
Sorry, I have also one more question. In your previous slide, right? In terms of like identifying the neurons, the cluster of neurons.
Yeah.
Is the method for that like saliency match? Like how do you identify those actual neurons? I mean the parameters.
I'm not sure about that. I read a few literature review papers and the math was kind of confusing, but I mean I'm an undergrad student and the mind kind of
You don't have to apologize. I mean,
Yeah.
the whole point is like,
Yeah.
we want to direct ourselves to papers. And if you're going to do a project where you're interested in that line of study, then it behooves us to study more until we understand the math.
Okay, the best paper I would recommend, like you can dive through the references there, is the first paper because it was a very generalized paper that helped me to lead to a lot of other papers that I've used for this presentation.
So which paper is that? The R plus 24?
How do I go back? Okay, computer science, computer engineering student not able to figure out. So,
This topic.
okay, this one. Build your own knowledge build your own knowledge and towards continual context learning was also very great towards methods, but it's a bit old because it was written in 2022 and a lot of the models that it used were slightly older, but it still has some great information about the challenges that you face and the kind of prompt engineering techniques that you can use to sort of test out whether the model knows the information or not.
Okay, that's Sahej for this.
Oh, you skip.
What?
You skip myself.
Go back to the writing section. Okay. It's okay, we didn't catastrophically, yes, we recovered in time, how's that? Let's put an optimistic spin on things.
Adaptive learning.
Adaptive learning, yeah. Okay, again, there are some questions and points that Taka has raised on Slack, so you're welcome to engage on that as well. Over the Jiaying.
So let's return a bit to the training phase of the model of the difficulty of data outbound. So let's first talk about like large language models capabilities and scaling. So scaling, we can scale up in either the training data set size or the parameter size. So existing work has conducted experiments on a large scale web test to Cobra and shows that the transformer-based language models performance improves significantly with either larger training data set or larger model sizes in terms of parameters. So what is necessary for this high performance? So as we can see here, like on the left-hand side, the model sizes, as models evolve, the sizes have grown in billions of parameters. And also on the middle side, in the middle of this slide, as we can see in the data sizes. So to train these larger models, we also have an increasing need for large-scale pre-training Cobra. For instance, from birth only 16 gigabytes to GPT 570 gigabytes. So where do we get all this data? Now, this large language model pre-training relies on some large-scale web scrape Cobra, such as Common Core, which is a publicly available web archive that provides web extracted text by removing the markup and other non-text content from the script HTML plus. So large language models, part of the reason why they can perform so well based on training from this data is that large language models can memorize information from the data. So existing work probes the trends for large language models memorization behavior, and they make 3 key findings. Firstly, larger models can memorize a larger fraction of the training data set. And then secondly, like examples that are repeated more often are more likely to be extractable from a pre-trained LLM. So this one is quite natural, as we can see. Assume like in real life, we witness something, we see some facts a lot more times than the others. So that will make us more familiar with the things that pop up more. And thirdly, the ability to extract memorized text can increase with the number of tokens in context. So by seeing the number of tokens in context, assume like we are given a book. So we want to prompt the large language model if it can memorize what is happening in the book. So we can either take the first 20, 50 tokens or say words, like let's say words for like just simplicity. We put in 20 or 20 words into the model, but because the 20 words is only like a more general, the model's continuations may still diverge. However, if we prompt the model with 300 words, like an entire paragraph from one book, then it is more likely for the model to reproduce what is that book. So large language models in this way memorizes a lot of useful knowledge from the web scrape Cobra. Here I give 4 examples. First one, like there are Wikipedia, like the informational sites such as Wikipedia, which stores a lot of text. And secondly, like there are blogs such as people's like technology-related sharing or just web-related sharing. Thirdly, there are forums where people can actually have this crowd wisdom from their discussions. And then lastly, there is GitHub, for instance, like code bases. So if models they see a lot of code and then memorize the code patterns, then they can eventually learn how to code. So the cutting-edge LLMs have been partly built on this collection of millions of books, articles, online chats, and other contents posted on the web. But large language models can also memorize other things from the corpus. So there are 3 undesirable examples. The first type is undesirable content. For instance, online we can see there are hate speech, like people that are cursing each other in some online platforms. And there are also some explicit content if we just scrape open from the web. So one existing work uses hate speech detection approaches to go through the retraining test and find that actually the presence of toxic content in common crowd is like 2 to 4%. And still, like in graph matching, we also find that some undesirable explicit content such as adult movie sites are also present in LLMs. So secondly, there are a lot of personally identifiable information online. Assume like there are some address books which actually contains the valid addresses like both email and physical, and also some phone number stuff. So research shown that if we just prompt inject, if we attack the model through prompt injection, that is, instead of letting the model do our like real life conversations, we are prompting it in some way that is unnatural. For instance, we just ask the model to repeat the word point forever. And then like after a few times, the researchers find that the models can be prompted to actually produce some real information of people that they validate to be true, like to be information of actual people. So that is problem for large language models actually memorizing some very identifiable information and then producing them in the inference stage. And the third part is copyrighted content. So this part touches upon the legal side of the story. So for instance, a lot of the some existing large language models, the most representative one is Meta's Llama model. They are trained using the book3 dataset. However, because the dataset contains a large amount of pirated books, like the company has since faced the lawsuits by the authors whose book has been like showing the pirated content. So this is actually not just a concern by the authors, like it's not just a random concern by the authors. Because existing work shows that, for instance, if we give the model a prompt, as shown in the prefix, and the target, like as shown by the as highlighted in red, is what is present in the original books. So if we prompt the model with an excerpt of the book and then ask it to continue, it can actually memorize the books near verbatim, as we can see what is highlighted in the green content. So then we arrive at the problem, like the key problem of how can we opt out all of this sensitive data, like the undesirable data, the copyrighted data, and also the personal identifiers. So one way researchers call is to unlearn. So recall that the training of LLMs usually rewards the model for repeating what is present in the data. So for unlearning, assume we want to unlearn the information about the person, we just flip the sign that's corresponding to this piece of information and punish the model for repeating certain sequences related to this information. So then the model becomes less likely to remember this concept or say out of the heart. But there's one problem. We need to define what needs to be unlearned in advance. So they are just due to the sheer volume of sensitive data. Like firstly, they are so abundant, and secondly, like it is unknown what specific like undesirable data are present in the data set. So it is impractical to exhaustively identify training data for removal under this proposed unlearning paradigm. So RAG on the other hand can enable flexible opting of sequences. So one representative work is this called silo language models, as referenced here below on this slide. So at training time, the authors propose to only train on the low risk data, which is from public domain and permissively licensed. At test time, they introduce large-scale data stores, which contain copyrighted, private, or say attribution-required data. So then the test time data store can be updated or say removed anytime due to different, say copyright settings or say different customization settings. And researchers, they actually find that say this score, like it refers to the complexity score. So the lower the better. So then the PD, PDSW, and PDSW-DY refers to 3 different cases where the authors only train the model on cognitive data. And PyDia as the baseline, it is a model of similar size, but it's trained mostly on non-cognitive data. So we can see that in some cases, the models can actually match the performance of the existing idea model. So that concludes my part, and now I will hand the stage over to our presenter for our Bottleneck.
So now I will present about prohibitively large model sizes of LLM. So we know that scaling models lead to improved performance. And overall, the vast majority of performance improvements in recent years is attributed to scaling compute. So this would be either increasing the model width and depth or increasing the token strain rather than algorithmic advances. And we know that flops is approximately equal to 6 times of the number of parameters as well as the number of tokens that it is trained on. And so if we take a look at this graph over here, the green portion represents compute scaling, and the blue portion represents algorithmic progress. And the green part has been shown more than the blue part. Additionally, for this particular graph over here, we can see that the number of flops, training flops required for models have become larger and larger. So I'll digress a little to talk about the scaling laws. So the original Kaplan scaling law suggested that as pre-training compute budget increases, the model size should be scaled more than the data. So given that you only have that much compute to work with, we should have a much larger model size than training data. So the original GPT-3 was trained on 300 billion tokens for 165 billion parameters. This is 1.75 billion tokens per parameter. Then later on, the chinchilla scaling laws basically showed that model size and tokens should scale linearly at about a 1-to-1 ratio. Later models showed that performance can actually improve if we go beyond this paradigm. So we can have more than a 1-to-1 ratio and have more tokens than parameters. So for example, Llama 1, 142 tokens per parameter, Llama 2, 284 tokens per parameter, and Llama 3, 1,875. I think the idea here is that we should still, the performance of models are still increasing due to either scaling of the size of the model or scaling the number of tokens of the model. As an example, I went to find the VRAM requirements for Llama 3.1. And as you can see here, as the model size increases, the VRAM requirements increases for inference. And we can also see how this increases for training or fine-tuning. Over here, this is from the Llama 3.1 solved by Hugging-based model page. And it says that if we wanted to run the largest model, we would need to run it in a multi-node setup or run it at a lower precision because it cannot be fit into a usual like H100 node. And this shows that if we are able to reduce the compute requirements, then there will be benefits. of course, not all the improvements in not all the improvements in performance is due to compute. So for example, mixture of experts and ensemble learning technique that improves performance without increasing training or inference costs. And we can see here that Llama 3 E8T2, which is the version with a mixture of experts, the amount of flops does not increase by much despite the large increase in total parameters. So in recent years, there has been a paradigm of scaling test time compute. However, this will still result in more computation. This might mean more flops in some cases. So this particular comment over here was given on Reddit by one of the engineers, and they indicated that although they had not run sort of experiment to figure out the difference in flops, but running Llama 3.2 3B 256 times is not as compute efficient as the 70B model. However, it is far more memory efficient. And so therefore there are some trade-offs, but I think the overall trend is that with bigger models, we will still need more computation. All right, I think that is the end of my section, and I think there is a little bit of summary at the end. Yeah.
Certain changes are not good then.
Yeah, you have to exit and reload this like that. Just click reload and it should come up. It won't do it on its own, yeah. See the new changes? The slideshow button's on the right.
Okay, so like now I wrap up the key takeaways from our lecture. So large language models, while they are very powerful, they can suffer 5 key bottlenecks as we have outlined earlier. So for instance, the input is for the model is to list the top 5 US states with the highest per capita GDP in order. So some parametric LLMs which are just pre-trained on a fixed data set, like although it's large-scale pre-training corpora, it may still make mistakes in that it mistakenly outputs the Fort and as California, but well, it wouldn't be the case. So speaking broader, factual inaccuracy is only one case of the large language model's bottleneck. Other bottlenecks also involve difficulty of verification, like how can we know the output of LLM is correct? Difficulty of data opt-out. If we want to remove some sensitive data from the large language model's training data, how can we do so? And the expensive cost to adapt. Nowadays, we can see the facts are also evolving with time, like who is the current US president. So the answer will differ from what it is asked 4 years ago. Also, so if we want to adapt to this ever-evolving knowledge, the costs are super expensive. And then finally, there's also this large model size problem. Like we cannot just keep scaling up the model sizes to them. So how do RAG assist those? How do RAG assist in addressing those bottlenecks? Let's start from the first one. Like RAG, firstly, it can enhance factual correctness. So the parts highlighted in yellow are the hallucinations of LLMs, which are seemingly correct, but are actually erroneous when compared with facts. However, if we use RAG token, also the FID RAG approaches, which incorporate retrieved knowledge from external trustworthy sources, we can correct which year the person is born and then what games the person played to make the outputs of the LLMs more factual. Secondly, RAG allows for inference time attributions. When we have output from LLM, how can we inspect what the information comes from and if the information is correct? So one method proposed by Google called governed cite, using retrieval, allows the model to actually give citations at inference time, what information it was using to produce this piece of response. So this allows for practitioners to actually check what is the output of LMs and then use it in a informed manner. So the Yajing enables flexible opting off sequences, like opting out and out there, like both the same like on the two sides. So we return to the pseudo language models as a representative case. So during training time, we can use only public domain permissively licensed data. Although that will limit performance, at test time, the large-scale data store can alleviate all the issues. If the data store is large enough, we can keep the copyrighted private attribution required data in this huge test time data store, which can be easily updated or removed anytime without hurting the performance of the model. And then the fourth case, IG enables better adaptability and customizability of the model. So here, like the question is, who is the current US president as of a certain time? So the answer to this question changes over time. But if we were to retrain the model, that would be too computationally intensive to consider. But if we focus on like using web search, like web retrieval, we use Wikipedia data. So Wikipedia data, if we search for US president, will tell us who is the current US president. So this is very resource efficient, yet it can allow the model to adapt to new knowledge or say new domains. And then lastly, IG leads to better parameter efficiency. So when existing work considers two pre-trained language models, like both Roberta large models. The first Roberta model is only pre-trained on it's pre-trained on a corpora, like it's pre-trained on web script corpora without retrieval. But the NPM is a variant of the Roberta model that incorporates retrieval. So take this like sentiment classification case. So both cases contains cheap, but the implication of cheap is different. In the first example, it only means inexpensive, but in the second example, like cheap construction, it is more complaining about the poor quality. So Roberta like just assumes the cheap to mean the same stuff and predicts positive sentiment to both, while the retrieval augmented sample, through retrieving the context that uses cheap in similar cases as the original example, can make correct prediction that the cheap construction is of negative sentiment. So that concludes today's course on what are LMs, what are the bottlenecks of LMs, and how IG helps to address the bottlenecks of LMs. So finally, I'd like to ask you to give another round of applause to the wonderful presentation team today. Thanks a lot. Any questions?
Well, I think we should spend about 5 to 10 minutes trying to digest, because it's important to bring it through the discussion. So Jiaying went through some of the key bottlenecks and how RAG can fix some of it. So do we have any comments? I know there was one comment on Zoom, but we didn't pick it up. And I entered Zoom a little too late to check it. But if there are any questions, please also raise that on the general channel, because the general channel can be digested by our scribes later on to document things into our proceedings. Are there questions? Again, those of you who are assigned to be more inquisitive, maybe you want to raise any points. Go ahead. Your name again?
Jonathan.
Sorry?
Jonathan.
Jonathan, yes. Go ahead.
Probably related with a very basic question regarding the factual inaccuracy, right?
Right.
I think in the internet data, right? It's more about probability, right? About the data instead of really factual facts. So how do we really can verify the factual in a way?
Okay, so Jonathan is asking, how do we verify facts that we retrieve, right?
Yeah.
Versus trusting the parametric model to give us the correct answer, right? Can I paraphrase it that way?
Oh no, well, sorry. What I try to say is actually the internet data we get is very much about the probability, right? So once it may be mentioned many times here, we probably assume it's factual, but it may not be true, right? So in that case here is actually, how do we even believe that it's very factual? Yeah, before even we talk about verification or this inaccurate verification.
Okay, so if we talk about retrieval models and how they decide which web pages to retrieve to you, right?
Yeah.
It is much more sophisticated than the math behind LLMs,
Mm.
that's for sure. There's a lot of signals that are bespoke and engineered in the IR community and also by search engine companies that allow them to rank web pages efficiently and well. Some of them you can't really do in an LLM. So for example, we will talk at the sort of the end of the course about source credibility assignment. Some of us are assigned to that task, right? So that's the task of saying whether a particular document, which might be retrieved by RAG, as a potential candidate for engineering an answer, is trustworthy or not, right? This is especially the case when your data store is something that you can't trust, like the web, right? Because the web has tons of documents that are created by bad actors that are loaded with keywords just to direct you to an e-commerce site to unload your money. Okay, so that's not what we want to serve. Like as Google, you don't want to lead people down that path because it will create negative reputation risk and cause you to lose market share, right? So they have this ulterior motive to keep you using Google by giving you high quality information, right? So that's part of the answer. How do you want to add anything to that? Maybe I forgot the spot for a second.
There just as a complementary example. I mean, for example, in the field of information retrieval, especially in the traditional days, especially the feature-based, when we quantify the quality or the relevance of candidate documents or web pages, there will be hundreds of features that can be used to justify the reliableness of the candidates documents or web. So there will be some. Yeah.
Let's also make it clear, these are not always algorithmic. Some of them are blacklist and whitelist. For example, in certain countries, you just cannot access certain things or certain phrases are disallowed, right? So these are not algorithmic decisions. They are rules decision designed in some type of whitelisting, blacklisting architecture to disallow indexing or retrieval of certain information, right? Because either the government or the rules that be allow or disallow information, right? Some of the other algorithms that are out there can engineer this, right? So if you know PageRank, which maybe at some point we'll cover in the course, allows you to calculate algorithmically the importance of a certain page based on what other pages point to it, right? This type of attribution graph-based algorithm, we currently don't have that technology within an LLM, right? An LLM, what we just see is text. There's no notion that which text is better than another. We only know that certain documents are longer and certain documents are shorter.
Yeah, exactly.
Right. So there are problems with having a parametric memory that doesn't assign credit, right? The only thing we can assign right now is credit in a probabilistic sense. If I see this word more, I see this n-gram more, then it's probably more likely that I want to serve that up again, right? But that has no correlation to trust, right? If I'm a child and my parents always say certain things all the time, I will learn to parrot those even though they're wrong, right?
Yeah, this is exactly in the medical field, right? So over the generations here, you may remember the whole knowledge of the previous generation to understand certain diseases here. But then it becomes a problem because all your knowledge, all 99% of knowledge is actually all generated.
Yeah, so on Slack, I also alluded to some of Taka's questions, so you guys can check that out if you have a chance. But many times when we want to edit the model or update an answer, it's important not to forget the answer that was previously there, right? So you can think of the cases where we had Twitter CEO example, if we completely forgot who the old CEO was, we wouldn't be able to answer certain questions anymore, right? So it's important to understand when that's the correct concept to evoke and when it's not, right? So some things that are factual knowledge, if you edit that out of the model, yes, you get the correct facts, but you lose indications that previously this was what we believe as a community or as a culture, right? So many times we thought the Euclidean model was the way to go for certain things, and now we don't believe certain parts of that model for certain aspects of physics, right? So that's one part that we can. Other questions that we have, I know we still have about 8 minutes, so online or in the classroom.
Yeah, we talk more about the model collapse. I'm very much curious about that. Someone more about that?
So who knows the term model collapse? Does anyone need an introduction? Okay, if you don't know.
I only know that if you train on too much synthetic data, instead of like human data, the model will collapse after some time.
Okay, so Yusong, do you want to elaborate on JF's answer?
Yeah, so the gentleman said that if we just always train on the synthetic data, then the model will become very boring or not useful, right? Okay.
Okay, so do we understand why that concept comes about? What is model collapse and why does it occur when you use synthetic data? So Jonathan is nodding no. So does anyone want to try to give an explanation? I mean, I can give one, but I would rather people in the class try to give explanations for what it is. First, what is model collapse? You guys are welcome to GPT it or yeah, I guess we don't use the verb Google anymore, right?
There's this saying, eating your own dog food. So it's like an LLM is producing data and then it consumes back the same data. It's not providing any new data. So, after a few generations of that, the most high probability distribution will get more and more amplified, whereas the rarer type of data gets filtered out. That's my understanding of it.
That's exactly correct, right? The model collapses to certain peak probabilities that are already highly peaky in the data, right? So it will start to forget and not be able to retrieve information that is less probable, right? So it can depend on what the model generates at the beginning, right? Because that's going to be reinforced because when you produce model outputs, if you use that as synthetic data to train the model again, you're enhancing the probabilistic choices that were made when you did inference, right? Inference requires you to decide between all of the different vocabulary words, choose some, right? According to the temperature, right? And does everyone understand temperature for this? Right? Temperature means like how much do you want to spread out going with the greedy selection of the correct next token versus having some stochasticity on choosing other things, right? So basically, when you're doing model collapse, you can think of it as doing a one round of inference and then turning the temperature to 0. Okay, does that make sense? Because then everything that you're going to generate just obeys the same probabilistic distribution as what you've already had, right? And that means over the long run, it will only be able to do that one. Okay, so I wrote on Slack a little bit. Model collapse was observed mostly at the beginning under the computer vision community. Okay, so they observed that in certain cases, when you have images that are initially quite distinct, right? Like poodles and parrot, things like that. But you start to simulate the data and augment it, that all of these collapse to a single category. It's no longer being able to discriminate these different classes because it's just going to gravitate to the center of gravity in creating an image. Does that make sense? So not necessarily vision, but diffusion models, to generate multiple images. So you want that diffusion model to be able to generate parrots, generate poodles, generate chocolate chip cookies or whatever, okay, as pictures. But after a while, because all of these things collapse to one, it can only generate one. Okay, so that's part of the problem that we have there. So it's important for models to be able to have more than one centroid to represent a particular class, right? So for example, in the case where there might be 10 animals that we want to recognize, if you just have a single model, it could gravitate towards one center of gravity, right? So all of the parameters will converge and we'll only eventually be able to generate pictures and recognize one class, right? Because we don't have the capability of distinguishing multiple classes within the same model. Okay. I'm not giving a very technically accurate definition. So if you'd like to question, please do.
Sorry, if like training language.
Again?
Sorry.
Your name?
Oh, I'm Zach.
Zach? Okay, yeah, I would
If-
want to ask a question.
If training like language models on their own inferences will lead to like model collapse, then doesn't that imply that those language models, like the tokens of lesser probability, were in fact the correct choice? Is that an implication?
Not necessarily. It could be that for the use case that you want, those answers that were created by the language model are the correct ones, and that's what you want to enforce, right? So it doesn't always have that output. But usually you think that there are a multitude of use cases and that the language model has to satisfy all of those use cases, right? So then you want to be able to not have model collapse. You want it to represent the true probability distribution where you expect users to want answers from all parts of that distribution, if that makes sense. Right? So in some sense, RAG is helping with that, okay, to bring it home again, because RAG allows you to externalize the probabilities into other systems that can help with that, right? So Jonathan asked earlier, how do I know whether to trust, the language model's output? Again, we don't currently have very good technology for that. I'm sure some of you in this room will invent that technology, okay? In part because there's plenty of work to do with language models, and there's a lot of things we can learn from information retrieval. It just hasn't been articulated into language models yet. Okay, so right now we are trusting retrieval agents, such as Google, such as Bing, such as Baidu, to use their own algorithms and their multitude of signals to pull up useful things. Okay. Now, in our projects, when we do any type of RAG system, where we're not trusting external search engines, but rather having a search engine locally, and you're more than welcome to try them. There are plenty of search engine solutions that you can find downloadable on the web. Haitao and myself can direct you to some of them. Okay. Those don't have all those nice safeguards engineered, right? They're basically just retrieval models. They don't have any authority or things like that to tell you whether a web page is good or not. It's just using information about n-grams pretty much to help you find the right topics. Okay. Other questions, Zach? How about online? Do any of you have questions online? We'll give you 10 seconds to unmute. Okay, so it's 8 o'clock. So we'll end our session today. So let's thank all of our presenters again. Okay, our support team will be doing all the post-lecture cleanup and scribing. So I can talk to you. For those in lecture 03 next week, you may want to stay back for a couple minutes to check on procedure. Okay.
Professor,
just coming tonight?
quick question.
Yes, go ahead.
If that's okay. Just so at the start of the meeting, you were talking about projects. maybe if like whenever you have time, if you could give some pointers on what could be a kind of a valid project, because of course like there's various people of various levels of expertise in the topic and in AI in general. So that would be really great in terms of kind of finding out what to do. Because right now for me, I don't have much compute, and I was looking at what kind of things like maybe some adaptive retrieval techniques and everything, what could be done. And so I thought maybe some guidance from you on that thing would really help.
Okay,
Kind
so
of
on the
hone in.
screen share right now, you see the project channel. So I hope those of you who are a bit more experienced and have ideas for projects can put your projects here. Okay, and then you can advertise your projects for other people to join. If you're not sure about what project you want to do, that's fine. We can also dialogue. I'm not sure. I don't have compute, but I have time and I can work on a project. So there are a couple different projects that I think are easy to do, and it depends on your appetite for putting in time. Okay, the first and most easy type of project is to reproduce other work that people have already done. Okay, that means go to GitHub, find a paper that's related to our course, okay, find the source code for that paper, download it, and try to run it. Okay, that can be very old models like Realm or FID that we introduced at the beginning. Okay, those I'm sure work because there have been plenty of replications of that. Okay, you may think, okay, just pushing a button and getting something to run is not sufficient, and you're be right. But even that is difficult many times because the environmental setup for those things are difficult. You have to install XYZ, put it into a container, all that's difficult. Okay, so again, projects are more about hands-on, dirty time to make sure that you have actually played with what you need to do. Okay, so that's the first part. If you find that's easy enough, okay, and you haven't consumed enough time, again, in our spreadsheet, you need to document that time. That is on the right side of the spreadsheet, okay, all the way over here. Okay, on this part, you can start to fill out this column that tells us what amount of hours you've used for the first 4 weeks to start doing your project. Okay, then you can start to do analysis, or you can read subsequent papers that follow up with that and then come up with ideas, right? You can use ChatGPT to come up with ideas. Like I read this paper, what else is interesting? Okay, and I definitely encourage you to use this class as a community. That's why we are trying to put all levels of students. Okay, use the project channel to connect. And again, at week 4, okay, 2 weeks from now, you need to have gone to the drive, okay, and fork the version of the slides for that. Okay, so if you can see here, there's the bookmark 1 that will lead you to the project title. It's not the right one, but similar to this, where you have to give a project title, your team members, and then try to answer some information about what the key metadata is. Okay, abstract of your project. Okay, a base paper that you've identified. If it's based on a paper, it doesn't have to be. Okay, and any pointers. Okay. So in week 4, myself and maybe Haitao will be meeting with some of you before class so that we can help you shape your project. Again, it's always better to have a smaller project than a larger project. Okay, does that answer your question?
Yes, Professor. Thank you. I'll be leveraging the community properly. Thank you. This will help.
Any other questions in class? Okay, I think we did a really good job of keeping time. I wasted the last 10 minutes, so sorry about that. So we'll excuse all of us for class today. See you next week.
It's fine.